All right, good morning, everyone. Please say hi if you're in the chat. Looking forward to chatting a little bit today about the ideas of energy, and then we'll talk a little bit about some stuff that they call thermodynamics, which is the study of heat and temperature and that sort of stuff. So, good morning. Hope everything is going well. I haven't had a chance to look at the labs that you were turning in on Tuesday, but I hope that went well. Please, if you have any comments about how things are working. Hi, Michael. How's it going? If you have comments on how things are working or anything like that, please let me know. I did get the exams for you graded. I think they went pretty well. It seemed like there weren't too many problems. I may have had one student. Good morning, Avery. Also had one student, it looked like they didn't put anything in for the calculational ones, so I'll be contacting them via email to make sure that that they didn't miss out on some of the things. So, but overall it looked pretty good, I think. Let's see if I have a quick look at the average test. Let me see what that looked like. I think it went okay, though. It seemed like it worked out all right, and let's see if I can find it. Where's our... There it is, exam 2. If I look at that, the average was, I think overall it went pretty well. Let's see. Average was about 81%, that's better than a typical exam. So I'll take that, considering the circumstances. But if you individually had an issue with how the exam worked out, please let me know, and we could do better, because we'll have of course, there's going to have to be other exams coming, so we'll have to make adjustments if they need making there. So please let me know in the comments or on the discussion boards, either comments or discussion boards on D2L, how well you think it's going. Apologize for the little bit of a hiccup on the scheduling of the stream for this week. I didn't think I had myself double booked on that, but my modern physics crew would have. Was who I had intended to have Wednesday's stream for at 10 a.m. So I could have, I suppose, merged the two streams, but I think the two groups are pretty far apart in regard to what sort of content you'd be looking at. They were looking at relativity and quantum mechanics, and you all are working on a lot of temperature and energy. So I think it would have been pretty confusing, not very worthwhile for folks. But so if you have questions on the material that we covered for this week, please post them in the chat, and I'll get to it. I'll talk a little bit about about what we're looking at for this week, just to give you an overview of stuff, and then. But I'd really rather just answer your questions. I'd rather just be a Q&A rather than me expounding on physics for you for the next hour or so. So I guess I will talk a little bit about how things look as far as content goes right now, and then we'll and then hopefully there'll be just questions, and I'll just pause in my my talk and let you get your questions in so I can answer them. So the first basic idea was the idea of from Monday was the simple harmonic motion idea, and that is basically the situation where you've got a mass and a spring. So say I've got a horizontal that's supposed to be horizontal. Imagine that it's horizontal, and I got maybe a wall over here, and then attached to the wall I've got a spring. So I got the coils of a spring or something like that, and then I have a block that has some mass attached to it there. So just to give you a sense about how this works, then, and this is what we talked about at the end of last week. We said, all right, so this mass has a spring constant associated with it, which tells us how stiff the spring is that's attached to the wall. And then because of the way that the spring works, the more you stretch it or the more you compress it, the bigger the force that it exerts on the mass. It gives rise to an elastic potential energy that's 1/2 kx squared. So I'll just write that here. That the elastic potential energy, I'll put a little E to indicate, that doesn't look like an E very well, but we'll fix it so it's a little, I guess I'll use a capital E just so it's, let's use a small e just because I want to distinguish it from energy. So that's almost better. So this is the elastic potential energy. The formula for it's 1/2 times the spring constant, which tells you how stiff the spring is, times x squared, where x is the amount of stretch or compression of the string. The spring. So the situation then is, if I consider the idea of conservation of energy, you can kind of see that this mass would undergo an oscillating motion. So if I stretch the mass, or stretch the spring by pulling the mass to the right here, what I would see is, if I release it from rest, or when I release it, if I'm holding it there, there's a certain amount of elastic potential energy that the spring has, and then the kinetic energy of the spring is 0, or the mass that's attached to the spring is 0. So if I let it go, then energy gets converted from elastic potential energy into kinetic energy. And there's a point where it reaches the spot where the spring is neither stretched nor compressed. There's a point there where there's no elastic potential energy because the spring is neither stretched nor compressed, so x is 0. All of the energy had then converted into kinetic energy, 1/2 mv squared. So the mass would be moving fastest here. And then after that, the mass sort of continues moving to the left because it has a velocity to the left. It continues moving to the left. And what happens then is the mass gets slowed down because it's compressing the spring. So it gives up its kinetic energy, and the spring gains elastic potential energy, so the spring becomes more and more compressed. So even though x becomes negative here, when you square it, you get a positive number. You get more and more elastic potential energy as you compress the spring. Then eventually you get to the point where all of the kinetic energy gets converted back into elastic potential energy, and the spring is moved the farthest to the left that it can go, and stops. But it doesn't stay stopped because the spring pushes it back to the right, and it moves back and forth. So it'll just continually trade elastic potential energy for kinetic energy, and back and forth between those two, and it'll just oscillate back and forth with a particular time. So harmonic motion, simple harmonic motion, is a way that works is using a mass on a spring as your example. So it takes a certain amount of time to complete an oscillation then, to go from where it starts back and complete a full oscillation and come back to exactly the way it was before. And the time that it takes to complete that full oscillation is called the period. We use capital T to indicate that. So the period is the time that it takes to complete one full oscillation and get back to the exact same situation it was before. Notice, this is especially important for that example problem that we did. If you release a mass from rest and you let it go to the opposite side, it stops. The time that it takes to do that is not the period of oscillation, because it's not where it was before. It's not where it started. It stops over here. It has to go all the way back and complete a full oscillation for it to be measured as the period. So if you start your stopwatch and let it go, and when the mass returns back to the spot over here where it started, that would be one full oscillation. So that's the time period. Then the frequency of the oscillation, small f, is the reciprocal of the period. The frequency being measured in 1/seconds. Temperature. If the time period here is measured in seconds, then the frequency is measured in 1/seconds, which the same thing. So 1/second, or that's oscillations per second. It's the same thing as the Hertz. It's named after Heinrich Hertz. There's his full name. 1 cycle per second is called a Hertz, which is abbreviated capital H, little z, which that you might have heard of. Like Hertz is in addition to it being a rental car company, it's the time, or it expresses the unit of the cycle per second, the oscillation per second. You may have heard of it in the context of radio or electricity or anything that oscillates. So, like in radio, if you're talking about, 93.7, the radio station, that's actually 93.7 megahertz. The radio signal that it sends out is a wave that oscillates 93.7 million oscillations per second, and that carrier signal is what makes what allows you to hear what's going on the radio. So, again, if you have questions, please ask them here if you want to see something specific. But that basically summarizes the idea of simple harmonic motion, which was the subject for Monday. the idea associated with that. So I guess I'll erase that because there don't seem to be any questions on that, and then we're going to talk about the idea of energy, but a different style of energy. So I guess since I don't see any questions popping up, I'm going to erase this one, and we'll talk about the idea of temperature. So what we've been talking about so far is the idea of mechanical energy. That was last week's topic at the beginning of this week's topic on Monday. This idea of mechanical energy, that an object has work done on it. It has kinetic energy associated with that work. It has potential energy associated with the position in a force field that it experiences, and all that sort of stuff. And this mechanical energy is the overall energy that the object has because of its motion or the position of the entire object. But in addition to that, there's microscopic energy inside the object itself, which has to do with the motion of the molecules and atoms that the object is made out of. So there's this internal energy. It's not the motion of the whole object that matters, or the position of the object, or the speed of the whole the object as a whole, but it's the internal energy is the energy associated with the motion and position of the tiny little atoms that the object is made out of. And one way to characterize that internal energy is the temperature of the object. So basically that is a measurement, that internal energy, the temperature at least of the object, is sort of a measure of the average kinetic energy of the tiny little molecules inside, molecules and atoms, I suppose, depending on what substance we're talking about, inside of the substance itself. So that's what temperature on a microscopic level means. Now that might be something new to you. Maybe you didn't think about what temperature is. It's just for you, if you haven't been thinking about that necessarily, its temperature is just, well, I feel the top of this book, or I've got my tea today, so the side of my cup is pretty warm. It has a high temperature. But that's really what's going on, is whether the side of my cup is warm is because the hot water that the tea is made out of is bumping into, those little molecules are bumping into the side of the wall of the coffee cup, and what it does is when those collisions happen, they give a little bit of their energy, their kinetic energy in the collision. They bump the molecules in the coffee cup and they make them wiggle and vibrate and that sort of stuff, and it raises the molecules' kinetic energy inside the cup, which means I can then feel that as a higher temperature of the cup. I notice that. So the way that you can notice something like that something has a different temperature, is because of the exchange of heat between. So if I touch the coffee cup, there's heat coming out of the coffee cup that ends up in my fingers and raises the temperature of my fingers by increasing the kinetic energy of the molecules that my fingers are made out of. So heating, that idea of heating, is an exchange of energy between objects that have two different temperatures, have two different average kinetic energies for the molecules that are inside. So that's what temperature really means. Now it turns out that there's a whole bunch of properties of objects that depend on their temperature. Like one thing that you may have noticed, and you hear about this all the time with in the summertime, sometimes the temperature of the asphalt of roadways gets so hot that they expand and they buckle, they rupture and stuff like that, and then they gotta go out there and fix that. But that's because the physical property of the asphalt, its volume, its length, its size of the actual asphalt, the roadway itself, depends on its temperature. The higher the temperature, the longer it gets. And this is how we look at objects and can sort of actually measure the temperature of those different objects by looking at their properties. So a regular old mercury thermometer, like a standard glass tube that's got some mercury in it or something like that, you got this little filament of mercury, and what happens is the volume of the mercury inside of that little filament, that little tube inside of the glass, that volume depends on what temperature it is. And the higher the temperature, the larger the volume of the mercury will be, so it goes up. So all you do is you say, well, I know how much mercury in it, and I know for each temperature there will be a particular length of the height, particular height for the column of mercury, and I put a temperature on the side of the thermometer, which indicates that length of mercury corresponds to 57 degrees Fahrenheit. And if it's higher temperature, it'll be a little bit longer. Maybe it goes all the way up to 60 degrees Fahrenheit for temperature and all that sort of stuff. So what happens then is we say there's this sort of what we call the zeroth law of thermodynamics, which is it's sort of the basis for all of thermodynamics. It's that when the physical properties that an object, so if one object is in thermal contact, which means they're allowed to exchange heat, like when my hand touches the side of my coffee cup, there's an exchange of heat between my hand and the coffee cup. This is pretty warm. So they're not in thermal equilibrium then because they're not at the same temperature, and that's what we're talking about. It says if the properties of the object change with temperature, and what I'm going to do is I'm going to put the two objects in thermal contact, then when the properties of the two objects stop changing, then at that moment they're said to be in thermal equilibrium with one another, which means that the two objects now have the same temperature. So this happens like if you take a mercury thermometer, like let's say you're going to take your temperature, the temperature of you, make sure you're not sick or whatever. I guess that's on our minds these days. You take a thermometer, you put it under your tongue. Now, what's going on now is your mouth is at a higher temperature than the thermometer probably. So what happens is the mercury thermometer changes its length. Now, while it's changing its length, it's not yet come to the same temperature as the inside of your mouth is. Eventually, the temperature stops, or the length of the mercury thermometer stops, and that's the time that we know that the two objects are in thermal equilibrium and they have the same temperature. So now the temperature of the mercury matches the temperature of the inside of your mouth, and then when you bring out the thermometer and look at it, you say, okay, your temperature is 98.6 because the temperature of the thermometer is reading is that. So that's what we mean by the idea of thermal equilibrium, and that sort of defines how we can measure temperature. So hopefully that's sort of a useful idea. That's sort of the plan. So that's the zeroth law of thermodynamics. Now the different temperature scales that we use we use three basic scales, and there's the Fahrenheit scale, which is sort of the Old English scale. It's a scale that we use here in the United States that practically no one else in the world really uses. And that's the temperature scale that we use every day. When we talk about the weather, the temperature outside, if it's 32 degrees, that's freezing. That's the temperature at which water will freeze or ice will melt. That's the temperature of transition. Water boils at 212 degrees Fahrenheit. And 0 degrees Fahrenheit is just a really cold temperature, but it's not special with regard to particular physical properties. Celsius scale is sort of based on the freezing and vaporization point of water, because 0 degrees Celsius is the same as 32 degrees Fahrenheit, and 100 degrees Celsius is the temperature at which water will boil or steam will condense into water. It's that point. So that's our two temperature scales. Notice they have different scales. So in the Fahrenheit scale, degrees Fahrenheit, to go from 32 degrees Fahrenheit to boiling, which is 212 degrees Fahrenheit, that's a difference in temperature of 180 degrees. In Celsius, you go from 0 degrees Celsius, and it's the same temperature at 100 degrees Celsius. It's the temperature at which water boils. So notice that in going from 32 to 212, that's 180 degrees. In going from 0 to 100 in Celsius, that's only 100 degrees. So the Fahrenheit degree is smaller. There's more of them in that same temperature span. There's 180 Fahrenheit degrees to go between the same two temperatures, the temperature at which water freezes and boils. And it only takes Celsius 100. So 100 degrees Celsius is, the degree Celsius is bigger in size than the Fahrenheit degree. So a difference in temperature of equal numbers of degrees in Fahrenheit and Celsius, the Celsius change would be a larger change in temperature. And I mentioned one other one, the Kelvin. This is actually not a degree. You don't say degrees Kelvin. It's just the temperature is measured in kelvins. The Kelvin scale is just the Celsius scale, but dropped by 273.15 degrees Celsius. So the Kelvin, so absolute zero is, and which we'll talk about in just a second, absolute zero is 0 Kelvin. That corresponds to negative 273.15 degrees Celsius. Really, really cold. Okay, so this absolute zero is like the coldest you could possibly get. And where does this idea of absolute zero come from? It comes from the idea of gases, actually. So and I had a little bit in the lecture notes about what the Kelvin scale really means. So one property of a gas that we know about is its pressure. So if I have a pressure, a gas that's in a particular contained volume, so I've got it in a vessel, in a cup, in a container, and it's a sealed container, and I have a little pressure meter inside that container. And then what I do is I say, well, I've got a temperature. I can take temperature away. I can I can refrigerate this container so the gas gets cooler. So what I notice is, if I put the gas in a container and I look at what pressure for that volume of gas that I put in there, pressure is going to be some value. Now, cool it. And what I'll notice is that the gas pressure will decrease as the temperature of the gas is decreased. And it'll do so at a particular rate. Okay, so I'm going to sort of draw the graph. This is kind of what we have. Okay, so what I do is I say, well, here's the pressure, the gas pressure that's produced, and then here's the temperature of the gas. So I start out for my gas and say I have a particular gas and I measure its pressure at a particular temperature is this value right here. So I plot it. And I say, well, let's lower the temperature. And I find, well, if I put it, here, if I lower the temperature to this value here, the pressure goes down to this. And if I keep doing the same thing, I'll find that eventually, this isn't exactly at the right spot, but just imagine if I lower the temperature even further, it does that. So it's following this trend line, which goes down like this. Okay. Now, I can't keep cooling it down forever, but it turns out if I take a different gas and I put it in there and I say, well, let's do this experiment again, okay, what I find is that gas might have a pressure at this temperature here, this value. And then the other thing that I notice is, well, now it does, if I lower the temperature by the same amount, pressure might not go down as much, and so on and so forth. And what I find is that if I get this, that there will be a spot where, this isn't exactly right, but a spot where the two will where the pressure will go to zero at a particular temperature. That temperature for which that occurs, we're just going to call absolute zero. Now, I put this in, I made it here so the two would both extrapolate down to a pressure of zero at a temperature of zero. So this temperature here that I'm measuring it in, it's the kelvins. It's the Kelvin scale. If I'd been doing it in Celsius, it would have come for a temperature which is a huge negative number. The pressure wouldn't hit zero for it until a huge negative number. So that's how they determined what absolute zero was. So the reason they call it absolute zero is because absolutely every gas does this. It works. It's the zero temperature for every possible gas. Okay. So far, there have been no questions, and I've just been doing a lot of talking. Hopefully, it's been relatively clear. But I want to make sure that I'm answering what you want to hear about. So I guess if you have questions, it's a good time to ask them. Anytime's a good time to ask them. You can stop me or whatever, and make it your question and answer series. Time, not just me just talking. So are there any questions? If you have no questions, just say none at this time, and I'll just keep going on. Or you could just tell me, hey, could you talk about the first law of thermodynamics, or could you talk about how to do conversions? Question 2 from homework 23. Okay, there we go. Now we got some. That's better than me just gabbing. Thanks, Avery. All right, question number 2 from homework 23. I have to check which homework 23 what we're talking about here for homework 23. I don't remember which one is which here, so that's the second homework set. Let me look here. We'll preview it. All right. I'm just going to look at it. All right, question 2. Is it the second question or is it Q2? I want to make sure that we're answering the same one. Is it the one with which spans the greater temperature range, or are we talking about when you place, is it a reliable procedure when you're checking somebody's fever to use your hand? Okay, Q2 in the book. Okay, thanks. Okay, and then Michael, I'll get to your question once Avery's is answered. Okay, so Q2 in the book, it says, which spans a greater range in temperature? A change in temperature of 10 degrees, 10 Fahrenheit degrees, or a change of 10 Celsius degrees? Okay, and that corresponds to what I was sort of talking about right here, Avery. 32 degrees, so in this case, the 32 degrees Fahrenheit and 0 degrees Celsius, as an example, those are the same temperature, really. It's this, if I walk outside and I say it's 0 degrees Celsius, and I walked outside and I said it's 32 degrees Fahrenheit, it's the same air temperature. It's just I'm expressing it in different units. So this is the same temperature. Notice in going between these two identical temperatures, going from this temperature where water freezes up to the temperature where water boils, that's 180 degrees Fahrenheit. Between 32 and 212. 180 degrees to go between those two. But to go from water freezing to water boiling, in Celsius, that's only 100 degrees. So it's asking you then, which spans a greater range in temperature? Now these are the two same temperature. It takes 180 degrees in Fahrenheit to span these two temperatures, but it only takes 100 degrees Celsius to do so. So think about that and see what do you think? Is 10 Fahrenheit degrees temperature change as big or bigger than 10 degrees Celsius? Okay, so hopefully that's a clarifying thing, and that's what Q2 is asking about. Okay. So hopefully that's clear. Avery, say if it's not and I need to do a little bit more. And then we'll get to Michael's question I'm going to start Michael's question okay, good. I'm glad that was helpful. Okay. So then Michael's question is, how do you solve the example problem from the lecture notes from 417 where you have a 100-gram ice cube is at 0 degrees Celsius? How many calories of heat would it take to melt? Okay, on and so forth. Yep. All right, so let me look back at that question, that example problem quick, just so that I have all the deets associated with it. All right, from 417. All right, so this is an example problem from the lecture notes for Friday, which is good thinking here. Okay, so this uses the idea of latent heat and the idea of work and all that sort of stuff. So I'm looking at the example problem right now. It says I have a 100-gram ice cube. It's at 0 degrees Celsius. How many calories of heat would it take to melt this ice cube, and then after that raise the resulting water to room temperature of about 22 degrees Celsius? That's room temperature is right around 22 degrees Celsius. So that's the same thing as about 72 Fahrenheit. Then it says the latent heat of fusion of ice is 79.7 calories per gram, and the specific heat of water is 1.00 calories per gram degree Celsius. Okay, so the way to look at this one is you got to look at it in two stages. So I guess I will get this out of the way as well because we don't have to worry about these conversions. So I don't seem to have too much issue with that. But I got a little ice cube here. Okay, let's kind of draw it because, why not? Okay, here's our ice cube. And the mass of the ice cube, the mass of the water inside of the ice cube. Now, I want you to also sort of notice this. That if you were to take this ice cube and melt it, the mass of the water, if you would measure the mass of the water, put it in a cup and measure its mass, it's the same mass. You don't lose any mass by melting the water. It's still the same number of molecules, the same number of protons, neutrons, and electrons. It's the same mass inside of a cube. It's just how they're arranged. Are they arranged into a liquid or are they arranged into a solid? So it's going to be the same mass throughout this whole process. Okay. So it says, all right, so the first thing we have to do is we have to melt this. And the idea is that there is heat associated with this, and we use capital Q as our thing for heating. And in my example, in the solution of the example, I said, well, there's some heat that needs to be exchanged between the air and the ice, for instance, to melt this ice cube and turn it into water. So this is the heat that has to be exchanged with the air. It's the energy that the thermal energy cube needs to break all of the water-to-water bonds that make this a solid. So I'm breaking all those bonds. It takes a little bit of energy, I got to do a little bit of work to break every one of those bonds and turn the crystal ice into liquid water. So there's a way that we talk about how to calculate how much heat that needs to be. In fact, it's the mass that I need. It's how many grams of water. That tells you how many bonds. There's so many bonds in each gram of water. It's not a different amount for each one. Every gram of water requires L sub F, the latent heat of fusion of ice. And what that is let's see if I remember right, 79.7. Okay, so for every gram of ice, I need 79.7 calories of heat to melt that gram of ice. Now, I don't have 1 gram of ice. I have 100 grams of ice. So I'm going to need more heat to melt the ice. And that's why to find out how much heat you need, you multiply the mass times the latent heat of fusion is what they call it. Which is basically a measure of how many calories for every gram would I have to take, what I have to have to melt 1 gram of ice. So this is calories, which I'll abbreviate CAL, per gram of ice. So that's what the latent heat of fusion is. Okay, now every state of matter has its own heat that is required to make that change of state. The latent heat of fusion is for melting or freezing. So it's how much heat you have to take away from a liquid to change it into a solid, or it's the amount of, if I have a solid, it's the amount of heat you have to add for every gram to turn the solid into a liquid. There's also the latent heat of vaporization. Latent heat of vaporization is how much heat it takes to take a liquid and turn it into a gas, or vice versa, is how much you have to take away. So the number we have here is it's 100 times 79.7. That is 7,970 calories. It's an A. There we go. 7,970 calories. So that's how much heat it takes to take this 0 degrees Celsius piece of ice and turn it into 100 grams of 0 degrees Celsius water. The temperature of the ice and the water doesn't change in this process. This is just how much work it takes to snip all the bonds. And the temperature of, you're not speeding up the molecules, the water molecules inside of the water just yet. You're just breaking the bonds between them. Okay, so that's how much you need to melt it. Now, the thing is, we're not done. We also, what we have here is then you've got a little puddle. All right, so there's the water puddle. Okay, there's the puddle water that the ice has been reduced to. So now I've got a bunch of 0 degrees Celsius water all melted, and it cost me 7,970 calories to do it. The thing is, I said, but we're not going to just leave the water here in a puddle here and let it stay at 0. We're saying, but we want to also raise the temperature of this water from 0 degrees Celsius up to 22 degrees Celsius, up to room temperature. So now there's some amount of heat that needs to be taken from the air, exchanged with the water, and give up some heat process. Okay, so this is the situation where this is how much heat it's going to take to warm the water. And that has to do with the specific heat. So, again, it depends on the mass. It depends on this. The C is called the specific heat capacity of the substance. So in this case, we're going to have to be talking about water. And then there's a delta capital T, where capital T here is the temperature. So this is how you calculate how much heat is required to produce a given temperature change once the substance is already all in the particular state of matter. So it's all liquid at this stage. How much heat has to go into the water to raise it from 0 degrees Celsius to 22 degrees Celsius? Okay, so again, it's the same mass. It's 100 grams. The specific heat capacity of water this is something you have to look up. Every substance is different. Actually, ice and liquid water have different heat capacities. Ice responds differently to exchange of heat. So if you got like really cold ice, like it's 30 degrees below zero, negative 30 Celsius ice, it's really cold, that's cold, and you want to get it to 0 degrees to get to, you actually have to add heat to warm up the ice before you can start melting it. It's always a two-stage process unless you're at the temperature. So that's why I said here is we started out with, in this case, the ice was already at 0 degrees Celsius and we were ready to melt it. But now that we got water, we use the specific heat capacity of water, which is 1.00. That's calories per gram degree Celsius of temperature difference. Okay, and now the thing is, I've got the change in the temperature that I want to affect. Well, I want the final temperature to be 22, and the starting temperature was 0. So the difference in temperature here is 22 degrees Celsius. Because I'm going from 0 to 22. It's not just the final temperature. It kind of looks like it here. But what if it was already at 18 degrees Celsius, and I only wanted to get from 18 to 22, the change in the temperature would be only 4 in that case. So this is always the change in the temperature. The final temperature you want minus the initial. Okay, so if I put this in, that's 100 times 1 times 22. I don't know, looks like 2200 to me is the number we get out of this. Okay, so now I look at how all the units work. Well, the grams here cancel out with the grams in the denominator of the specific heat capacity there. And then the degrees Celsius cancels out with the degrees Celsius here. And I'm left with calories. So to melt the ice takes 7,970 calories. To heat it up to room temperature from 0 degree water that's been melted to 22, it requires 2,200 calories. So the total is just the sum of those. So it'll be 7,970 plus 2,200. That looks like, that's 9. That looks like 1170. No, 9. It's like, I don't know. Let's see. It looks like 10. It looks, yeah, well, I'll just. It's 10,170. There we go. I knew I could do it. Carry the 1, right? 10,170 calories total. That's my answer. Does that make sense? Is that good, Michael? Any other examples folks would like to see? Or questions on homework that I can clarify for you? Okay, good. Glad it was helpful. So I have to think in terms of energy exchange here. And that's what's going on there. So let me talk a little bit about sort of lecture 3 while I wait for other questions to come in. Please ask questions right now. Just put it, if you got a question or something you want to see clarified, just ask it right now and I'll get to it. Because of the delay, it's a little bit awkward here. Okay, E17 from homework 22 part B. So E17. All right, let's see. E17. I think that's a chapter. That's not a heat one. That's a chapter 6 one, I think. E17 part B. Let's see. Okay, so right. So E17, Avery's asking is, so you got a 300, so I'll just read it so that folks sort of have a sense about what it is. We have a 300 gram mass lying on a frictionless table is attached to a horizontal spring that has a spring constant of 500 newtons per meter. The spring is stretched distance of 46 centimeters, which is 0.46 meters. The first question is, what is the initial potential energy of the system? And then part B is, this is the one that Avery's asking about, what is the kinetic energy of the system when the mass returns to the equilibrium position after being released? Okay, so you want to know what the kinetic energy looks like. So this is what I'm going to do. I'm going to get rid of this so we can have a little bit of space to work with here. I guess I'll get rid of that one too, because why not? Okay. So the idea is this. We've got the mass of spring. And let's say I'm going to draw the original position. So here's the mass way out here. And let's say here's the equilibrium position. This is if the spring was either stretched or compressed, the mass would be sitting here. But at this initial position, I've stretched it by, let me use a smaller size here so we don't, 0.46 meters it says. Okay, so 46 centimeters is the amount of stretch, so it's stretched. And it asks you, well, let's calculate how much, the first part of the question is, let's calculate the elastic potential energy that this thing has. But so this is sort of the before picture. This is the, the starting picture. So I'll put before here. Okay, that's supposed to be a E, there we go. And now let's look at what the after picture is, because it's asking about a different situation. It's not asking about what the situation looks like or the kinetic energy in this particular point. It wants to know, well, what is it like when, let's see, specifically it says, what is the kinetic energy of the system when the mass returns to the equilibrium position after being released? So now I'm at this situation here where I've got the spring is at its natural length. So notice again, I'm using the same scale as I used up there, trying to at least. And I say now the mass is at the equilibrium position. The spring is neither stretched nor compressed. And at this stage, there's a velocity that the mass has, because originally it was over here and stretched, and the spring has pulled it over here. What we would use here is to use the idea of conservation of energy. The initial energy here is a mixture of the kinetic energy that the mass has to start and the potential energy that it has to start. Okay? Now, the kinetic energy in this before situation, it's being released from rest. So at this moment, when it's 46 centimeters away, the kinetic energy is 0. The total mechanical energy is all on the elastic potential energy side of the ledger. That's what it's asking you to do. Now, the total mechanical energy in this after picture, this what we'll call the final picture. It's not actually final. It doesn't end at this point, but it's the one we're considering for the final. It's after. This will be, well, how much kinetic energy does it have? Plus, how much potential energy does it have at that particular moment? And I know that the total energy is the same both in the before picture and the after picture. The question is, for this case down here where I'm in the after picture, how much elastic potential energy is there? And I want you to remember that the general formula for the elastic potential energy is 1/2 times little k. This is not the kinetic energy, this is the spring constant, times x squared. Remember, x equals 0 is this spot right here. So I want you to think about that now, Avery. See if you can lock this down. How much potential energy does the mass have when it's at this particular position? Remember, x is 0. Okay, think about that. Now, if the total energy stayed the same between the initial and final, where did that elastic potential energy go? Hint. Okay? So you should be able to, you don't actually have to calculate using like 1/2 mv squared what the kinetic energy is, because you don't have a good sense about what the velocity is going to be. It might depend on the mass. Probably depends on the spring constant. Depends on all the forces acting. You don't have to worry about that though. It's just asking what the kinetic energy is. And if you can then make the comparison here, hey, where did all that elastic potential energy go that it started out with? Where did it go? You could probably make an inference about if the total energy was supposed to stay the same and I lost all my elastic potential energy, it probably went over here. Hopefully that helps. Does that make sense? Any other questions? Glad it was helpful. Anything else from folks? So while I'm waiting for questions, and again, don't hesitate. Just put them up here. If you got a question, just get it going because there's no reason to wait. I have no real great desire to just be talking. I'm just kind of trying to make use of what time we have to give you a little bit of context and background when I'm waiting for questions to pop up. But it's really about just the questions if we can make it like this. But I want to tie this idea of mechanical energy, which is kinetic plus potential energy, the whole mass, and the idea of work and stuff like that, to this idea of heat, which is coming later on. If you haven't looked at the lecture for Friday, just to make sure that that there's a connection there. So, one thing that was really, really important is back in the day, historically speaking, people, scientists thought of this idea of heat, and they thought of this idea of mechanical energy, like kinetic and potential energy that we have on the screen here, and they thought of them as very distinct things. They didn't think of them as so, and that's why we have these two different units of energy. One we have for heat, typical for heat, like calories, and then we have for mechanical energy, we got joules. But the reason it's called the joule is because Joule actually noticed that they're the same thing. That they're just two ways of writing the same thing out. In other words, he noticed that there was a mechanical equivalent of energy for heat, and that heat could be used to do work. And in other words, it wasn't just some weird process where heat turned into work and all that sort of stuff. It was just conservation of energy on with an eye towards something a little bit more global. Like heat is energy. Heat is an energy exchange. So what he figured out is that what we call the first law of thermodynamics. If a system, like a gas and a piston or something like that, receives or exchanges heat with its environment in some way, you could do work with it, and it would result in a change in the internal energy of the gas. This is actually the basis for the heat engine. This is the basic working principle of the heat engine. And we're not going to talk too much about heat engines and that sort of stuff, but we'll talk about it a little bit in this class, but just a little bit. So let's say that I have a gas that is inside of a piston or something like that, and then I add some heat to the gas. And one way you could do that is in the form of an internal combustion engine. What you could do is you could put some gas, dissolve it with air inside of a cylinder, and then you could add heat to the system by igniting the gas. So now there's some energy added to the system. So a little spark from the spark plug or something like that causes heat to be added to the system in the form of the explosion of the gas, the gasoline. The gas inside of the piston then rapidly expands. And it does some work on its surroundings. Okay? So by that I mean you could have that, the cylinder that's inside of this piston, or this piston that's inside of the cylinders, and you could cause an expansion of the gas inside of that, and it could push on the piston, and it could do work, like it could turn the crankshaft of your car. So it could do some work. So what this says is that whenever you add heat to a system, and you use that system to do work on its environment, the conservation of energy says that in this process where you do those two things, you could change the internal energy of the system. You could change the internal energy of the gas. So in other words, you could add heat to the system, but if at the same time the gas is asked to do work on the system, not all of that energy actually goes into changing the temperature of the gas, which is related to its internal energy, like we talked about earlier. Some of it is used to do work. So if I add heat and then subtract out some work done, the temperature of the gas won't go up by as much. Its internal energy won't increase by as much as if you didn't do any work. If you just add heat to the system and no work gets done by the gas, the process, the temperature of the gas just goes up. Okay? Or the other thing is you could say, well, I'm going to do work on the system, but I'm not going to give it any heat. So the work is there's going to be some work done by the gas. Well, what would that do? That would actually lower that energy's got to come from somewhere. It comes from the internal energy of the gas. So you would lower the temperature of the gas in that case. So this is the first law of thermodynamics, which is basically the idea of conservation of energy, taking into account the internal energy of the system. So there. So hopefully that sort of connects. This is why we can connect what we talked about in Chapter 6 with what we're talking about now in Chapter 10. And by the way, those other chapters we're just skipping. We're looking at the idea of energy and work, and they happen to be separated by some other chapters in the book. And that's where we're going with this. Okay. So I didn't see any other questions pop up from folks, but I just wanted to hopefully make it clear. I'm not sure that the lecture notes are always, if you maybe hear it a different way, it makes it a little clearer. Hopefully that's a relatively clear idea and give you a little bit of a real-world example of how stuff works. But are there any questions on homework or anything like that we need to consider? And then again, I'll add a little bit of context while I wait for your questions to pop up. So just ask. It doesn't have to be about this. It could be about anything you want. But I do want to talk a little bit about the signs of these numbers here that can go in. If heat is given to the system. Oh, Avery just came up. Question 10 from 24. So Q10 from 24. That sounds like out of Chapter 10. So homework. Q10 from homework 24. Q10. Okay, so that one says, and this is related to another example problem that's in there. So, good question here, Avery. So, two objects of the same mass made of different materials are initially at the same temperature. Okay, so equal amounts of heat are added to each object. Will the final temperature of two objects necessarily be the same? Okay, so let me make some, oops. Let's see, let's select here and we will clear some things out a little bit. So I have a little space to work. Okay. So I'm gonna say this. This is an important idea. That when heat is exchanged with an object, its temperature is going to change governed by this. Which we use this already in one of the example problems that Michael asked about. Okay, so this is sort of a cause-effect relationship, almost kind of like Newton's law. So I just want to make that as clear as I can. If heat is exchanged, it causes a change in temperature of the object, which depends on other properties of the object. The mass of the object that's receiving the heat and the specific heat capacity of the substance that the object is made out of. So plastic, glass, they have different heat capacities. Air has a different heat capacity than water does. Water has a different heat capacity than wood. I mean, they all, that's a substance, so the heat capacity is substance specific. And so they're different. It varies from substance to substance. So if you give a certain amount of heat, if you add a certain amount of heat to the object, so that's a positive Q, and that object has a particular mass, and then you look up what its heat capacity is, you'll be able to determine the temperature. In a lot of ways, I'll just write over here, just sort of, it's not really secret, but in a lot of ways, this looks like this. On one side, I have the cause. On the other hand, I have the effect. I have this force, and it acts on an object that has some properties. Properties we care about for Newton's second law was mass. And then it experiences an acceleration response to that. So here's a cause-effect relationship put in the form of an equation. This is the same sort of thing, except what's happening is the cause is I'm adding heat, or maybe I'm taking heat away. If I'm taking heat away, this Q would be negative. But if I'm exchanging some heat with the object, here's some properties of the object. This is the heat capacity, here's the mass. How much of the object and how much is it? So this is kind of like the mass in Newton's second law. And then the result, the change in the property of the object that happens, over here it's the acceleration, the object velocity change. Here, it's a change in temperature is what occurs. Okay, so what this is saying is, Q10, I got two objects, they happen to have the same mass. Okay, so this is the same. Okay, so M is the same. So I'm pointing just at the M, not necessarily at the C. Okay, but they're made of different materials. Okay, if they're made of different materials, then they're not guaranteed to have the same specific heat capacity. So the C can be different. In fact, it's very likely to be different. If two substances have the exact same heat capacity, that would be an incredible coincidence. Okay, very unusual for that to happen. Basically, every material has a different heat capacity associated with it. Okay, so then it says they're initially at the same temperature. Okay, so they start out at the same temperature. So I'll sort of rewrite, I'll just write this so we have what this sort of means. M times C. Delta T is the change in temperature. Another way to write that would be final temperature minus initial temperature. So we do know that the starting temperature is the same, but it's going to be asking about what happens with the finishing temperature. Okay. Then it said equal amounts of heat are added to each object. In other words, Q is also the same. So the amount of heat which is added to each object is the same. The amount of mass of each object is the same. The initial temperature of each object is the same. And it's asking if the final temperature is going to be the same. Well, there's one thing here which may not be the same. And remember, this is inequality. Q has got to be equal to MC times delta T. If M is the same but C isn't, then delta T won't be the same. That's a big hint, I know. It's probably more than a hint. But hopefully that gives you a sense about what matters here. Yes, I'm giving it the same amount. It's kind of like the same thing here. If I was to say I've got the same force applied to two objects, but the object had different masses, would they accelerate the same? No. The larger mass would accelerate less. So that's the same sort of thing here. Except it's not just the mass that heat and temperature care about. It's also this heat capacity thing. So hopefully that answers that one. Is that good? Any other questions too? Hopefully that answers it. I think it probably should, but if I need it to do a better clarification, just let me know, either Aiden or Michael. Okay, good. Anything else? I want to mention this too, so while I'm waiting for other questions to pop up, I know we're right at about an hour here, but I'm willing to go over if you have more questions. But I'll say this too. I mentioned this really briefly just now too. This heat that this can have, it could be positive or negative. If I add heat, if the exchange of heat with the system that we're talking about, the substance we're talking about, if I add heat to the system, that's positive. I'm adding heat to it. If I'm taking heat away from it, then Q would be negative. So if I take heat out of the system and add it to the air, so I'm taking it out of the object of temperature I'm talking about, well, then what happens? If Q is negative, well, the mass can't be negative, and the specific heat capacity, that's always a positive number, then delta T must be negative. Well, what happens if I take heat out of water or something like that? It cools down. Delta T ends up being negative because of that, which, because of this, you can see that if delta T was negative, that would mean the final temperature is smaller than the initial temperature. It's cooling off. So when Q is negative, that means the object is typically cooling off. I've taken heat out of the system, and that has reduced its temperature. Its internal energy is probably going down in the process as well. The only time the temperature wouldn't be going down when I'm taking heat out of the system is like if I'm at water's at 32 degrees Fahrenheit or 0 degrees Celsius. Then when I take heat out of the system, it actually causes the water to freeze rather than get colder. It doesn't start getting colder until all of that ice has dropped. All of the water, has turned into ice. And then the temperature of the ice, if I continue to take heat, the temperature of the ice goes down. Okay, anything else? We're sitting at right about an hour here, a little bit over an hour. But I want to make sure that all the questions are answered. Oops. Okay. So I'm going to say this, then we're going to call it here really quickly, but I did want to mention one thing too, because hopefully other folks are having a look at this in addition to you here. But you get the message here first if you want it. So what we're looking at for next week is we're going to finish chapter 10, and then that'll be the end of our unit. We're not going to go into chapter 11. We're not going to go into second law and entropy and that sort of stuff. It's relatively complicated and stuff like that. So these two chapters, chapter 6 and chapter 10, are going to constitute our entire unit, unit 3. So then we'll finish up at next week, and we'll have a review, and we're looking at another exam, exam 3, on chapters 6 and 10, sometime at the end of next week, possibly over the weekend. But of course I'm going to give you your review opportunity, and we'll have review material and stuff like that up, and of course I'll have a Q&A next week before whatever exam would open up. But it'll have the same sort of format as we had previously with the last exam. We'll put there'll be a set of multiple choice, a set of calculational questions and that sort of stuff, and then it'll be available for 2-3 days, something like that, to give you a chance. But it'll be timed still just like the other one. But just to give you a heads up that we're on the way for the next exam. We have a little bit, 2 more sections to cover out of chapter 10 before we call it, we call it done. But that's what I'm planning, is that end of next week will be exam number 3, and then we'll start with the final unit on electricity, which is a shift in gears again from kinematics to forces to, we'll get to unit 4. Okay. So I'm gonna call it then. I think it doesn't look like any other questions are popping up in the chat. Hopefully this was useful to you. Again, please use the discussion boards if you like to ask more questions and stuff like that. I didn't see any when I checked last night for any questions that popped up in the discussion boards for the live stream. So hopefully folks are getting their questions answered or understanding it pretty well. But I'm going to sign off for today. Hopefully you found this useful. I'll look forward to talking to you next week. I'll be a little bit more careful about what my schedule looks like for my live stream, so I make sure and don't double book myself like I did this week. But it was good seeing you all. Those that asked questions, hopefully that was helpful, and I'll see you next week. Goodbye for now.